another multivariate statistics class. And of course, I checked my calendar and I realized that this is the 10th week of the semester. And because of that, I want to slow down. I want to give students opportunity to have a recap on what they've done all the way from the start of the semester. Because of that, I'm not going to give new assignments this week. So I wanted to spend your time, trying to review what we've done so far, because this is week 10 of the semester. What I have for you this week, this is where we stop in multivariate linear regression. We're going to continue from there. Then when maybe after we're done with this, we're going to go over the multivariate version, and probably on Friday we start a new topic or principal component analysis. But like I said, if you have missed one or two assignments, probably you can reach out. I can give you a makeup for the assignment that you miss. So this is a week of slow down. Now I want to slow down a little bit to give you, and I'm also going to, the current assignment will be, the deadline will actually be extended. So today when I get to my office, I'm actually going to extend the submission until Wednesday deadline, okay? The assignment that was due last night. So like I said, there's no new assignment, but I want to give you this opportunity, your opportunity to, have a recap on what you've done so far. This is week 10. And I also gave information about group projects. I needed to check the announcement section. I released that last night. I'm actually going to assign you to a group. Okay, you're going to work with group, and I will assign you a topic or area, the area you're going to work on. So more information about that later. Okay, so we've been dealing with, we've been reviewing linear regression. The essence of what we're doing is actually because we want to generalize to multivariate regression where we got more than one dependent variable. So I've walked you through up to this moment. We've been able to specify the model, and not only that, I show you there's going to be some kind of theoretical work. I show you how you can derive, the maximum likelihood estimate of the parameters, okay, from the normal density. And, from the normal density. So what I'm trying to talk about is that if I have y equal x b plus the error as the model specification, and of course we've been able, and I said if f of y, if y follow normal distribution, we have 1 over square root of 2 pi sigma square exponential raised to power that y minus mu divided by sigma squared. And I remember I said that where the mu equal xb, because that is the expected value of y, okay, the expected value of y. So if I have that plus that, the other time I said this is going to be x plus the expected value of the error. And according to assumption, expected value of error equal to 0. So because of that, I'm actually saying that mu equal to that. So and my f of y will be square root of 2 pi sigma squared this sigma squared y minus xb squared. Okay, y minus xb squared. The xb is actually the mean in that regard. Okay, so now if xb is the mean in that regard, don't forget this is the model. Okay, this is the response variable against explanatory variable. Now, if I have this right now, and I want to, rewrite this in a matrix form, okay, and not only that, I want to find the likelihood of this because this is the PDF. I want to find the joint PDF. Okay, so if I want to actually, if I want to rewrite that, I'm actually going to have f of y. If I want to write this one in a matrix form, I'm having 2 pi sigma square raised to power minus n over 2, an exponential this sigma squared. Okay. Now, I'm going to have, okay, y minus xb, okay, transpose y minus xb. Okay, the transpose is coming, because of the square. Now, so and if you, that is exactly what we are. I'm going to show you. I'm going to walk you back into that because that is very, very crucial. Now, if you take a look at this guy now, okay, so splitting. So what you have here now is, I'm talking about, this is a likelihood function. Okay, this is a likelihood function. I want to write it in an n term. Okay, now if you take a look at this, I can do 2 pi raised to power minus n over 2 or sigma square raised to power that. Then I have that mathematically speaking. Is there anyone who want to ask question about that? Now, if you take a look at what I have, I'm assuming, because I want to estimate the parameter b. Okay, the intention is to estimate the parameter b. Give me 1 second. Okay, so the intention is to estimate the parameter b, okay, in a linear regression. This is the response, and I want to use the method of maximum likelihood. Okay, the method of maximum likelihood, I'm assuming normal distribution for the response, and of course I go by way of this. Okay, now if this is a log likelihood function, then I actually want to maximize. I want to use the method of maximum likelihood. Because of that, I'm going to introduce a log. Now, to introducing log, okay, log of that, f of yi, okay, the log of that, if I call that one here, the log of that, I'm actually going to have log 2 pi that plus log sigma squared that. Now, the log is a natural log. I'm just going to have this. I'm only going to have that. And of course, all of this guy, because it's independent of b, I'm going to call them constants, c. This is independent. So I'm going to write that as minus half sigma squared y minus this plus constants. What I mean by constant is that because it's independent of the parameter that I actually want to estimate. Now, that is what I have up to this moment. Okay, that's what I have up to this moment. Now, up to this moment now, what I need to do is to perform an antiderivative. Okay, I want to differentiate this guy with respect to b. Okay, I want to differentiate that guy with respect to b. So I want to differentiate that guy with respect to B. Okay, so I can still do the L, the B. Okay, the L, the B. I want to differentiate this guy with respect to B, and after doing that, I'm actually going to equate to 0 to solve for B. Okay, now if I want to differentiate, this guy with respect to B, when I did that, and I set that to 0, I'm actually going to get, you can try that, I'm actually going to get y prime y, okay, sorry, I'm going to get x prime x inverse x prime y at the end of the day. That's what I'm going to get, okay? So when I try to differentiate this guy. Now, based on that, based on what I have right now, okay, here, if you take a look at it that I said, B that I'm looking for, this very B is actually going to give me B0, B1, B2 until I get a BP, okay, which is going to be, P plus 1, okay, so which means the number of the parameter, including the intercept, is going to be P plus 1. Of course, we have B1 to BP is P, then plus 1. And that's why you can actually see, that's what I said at. Now, like I said, the final result is this guy here, okay? And you're actually going to put a cap because it's an estimator, okay? You put a cap because it's an estimator. Now, after that, now let me tell you this. Why am I spending my time on linear regression with one dependent variable and spending my time because if you understand the linear regression with one dependent variable, you will easily understand linear regression with multiple dependent variable. Okay? Now, do you know that based on, the other time, please, I need you to pay attention. The other time, when I was focusing on B, I did not consider this part. This part was regarded as constant. But, I may also be interested in estimating sigma squared. If I want to get the maximum likelihood estimate of the sigma squared, okay, so I'm actually, I'm going to come here, or I'm going to come here, okay, I'm going to come here, and I'm going to differentiate that, okay, I'm going to do DDL with respect to sigma squared, okay, DDL with respect to sigma squared. So when I do DDL with respect to sigma squared, I'm actually going to, this is what I'm going to obtain, okay? I'm actually going to obtain this guy, okay? I'm going to obtain that guy when I differentiated the whole of this with respect to sigma or sigma squared. You solve for, you equate that to 0. After doing that, you equate that to 0. Whether you do this or you do this, or you do the sigma, and you equate that to 0, okay, your final destination, what you're going to get is that. Okay, that guy is the MLE of sigma squared. So which means from the likelihood function, we can optimally derive the estimate of regression parameters. Not only that, we can also derive the maximum likelihood estimate of the sigma squared. Okay? So that is what I'm... Now, but let me tell you this. We have another estimate of sigma squared, okay, which is this guy. There are two estimates of sigma squared, okay? Now, the first one that I mentioned is the one that I call the maximum likelihood estimate, okay, of sigma squared. But we also have a sample, the estimate of sigma squared that we derive from sum of square error, which is this one. So when I have a sum of square error and I divide by n minus p minus 1, which what I'm dividing by here, the n minus p minus 1 is the degree of freedom for error. When I divide sum of square error by its degree of freedom, I'm actually going to have another estimate of error variance. Now, there are two error variance. Okay, now what I'm actually doing here, okay, but when you take a look at the two error variance, the one that we obtain dividing the sum of square error by its degree of freedom is unbiased. Okay, it's an unbiased one. Okay, why the one that we got through the MLE is biased. Okay, the one that we got through the MLE, and what I'm trying to do here is to be able to tell the world that it is actually biased, because if it is unbiased, it is required expected value of an, like for instance, if I have an estimator, if this guy is an estimator, expected value of an estimator should be equal to its parameter value for theta cap to be unbiased. Okay, but in the case of the error variance that we estimate using the sum of square error, it is biased. And this is, if I want to measure the amount of the bias, is what I'm doing here. The amount of the bias is to subtract the sigma squared from that, and this is the amount of the bias. Okay, this is the amount of the bias. If this is the amount of the bias, but do you know that if sample size is large, this guy is trying to say when the sample size is large, the whole thing will converges to 0. And that is one of the property of maximum likelihood. Okay, we call that property asymptotic property. Asymptotic property, so which means when sample size is large, the variance of an estimator converges to 0. Okay, so we call that consistency property in statistics. Okay, and that occur asymptotically. Asymptotically means when sample size is large. Now, there's going to be a kind of debate. Okay, which one should we use between the two estimates of variance in linear regression? Please, I need you to pay attention, because there can be a kind of debate of the one to use. Okay, there can be a kind of debate on the one to use. We have two estimates of variance. The one we got through the approach of maximum likelihood, and the one we got using the sum of square residual. Now, this is then, but let me tell you this, because because of efficiency, what I mean by efficiency in statistics, efficiency means lower variance. Okay, efficiency means lower variance. We can mathematically prove that the one that we obtain using the maximum likelihood estimation is going to be less than the estimate of variance that we derive from sum of square residual. Okay, and that was why I said that guy is going to be less than that. But the one from the what is it called? The one from the maximum likelihood estimation is biased. But when sample size is large, that biasedness can turn to 0. And when bias equal to 0, then it will be unbiased. So which means it may be biased at small sample, but when sample size is large, it's going to be unbiased. So we prefer it. Okay. Now, And I gave you ways to estimate that in R. Okay, you can see here, this is actually demonstrating how you can figure out the estimate of error variance. Okay, the one you obtain by dividing the sum of square residual by a degree of freedom is that. Why the second one is through the MLE. The second one is MLE, where you have that divided. You can see that the second one is MLE. Okay, this is how to program that in R. When you can see that, you can see in figure, this is smaller than that. That's why we prefer using the one, with the MLE. Okay, now the property continue. Please, I need you to pay attention. If you don't understand, ask question. You deserve the right to ask me question. Is there any question at this time? Okay, like I said, there's not going to be any new assignment this week. I want to slow down. I want you to review what you've done before. And if you get stuck, I need you to visit me in my office hour. My office hour is conducted remotely. You can join, the Zoom. The Zoom link is on Canvas. Now, I want you to see the summary of results. Now, given the module assumptions, we have that B cap, okay, follow normal distribution with the mean of these and the variance. Please pay attention. We got a lot of theoretical work today, And the moment you don't understand, I will advise you ask me a question. Now, I want to prove the first, second, and the third one. What if they ask you to prove this in exam? Okay. I want to prove that because the B cap, please pay attention, because this guy, okay, that we derived, okay, is an estimator. An estimator will give different results when you use it on different training data. And because of that, it's a random variable. This guy is a random variable. Then if it's a random variable, we can find the average. What is the average of this guy? What I want to show now, okay, when the average of this guy exists, I can also find its variance. Does that make sense? Now I want to find the average now. Finding the average is to take expectation. Expectation of this guy. Expectation of this guy is to take the expectation of what I have here. Like I said, if you don't understand any theoretical thing I'm doing on the board, ask question. Now, I want to take expectation now of this guy in linear regression. Okay, if you take a look at it, this is a combination of x and y. Anything x is assumed to be fixed, but y is random. And expectation is going to attract random. So because of that, I'm going to have this. You see that? Expectation only attracts response variable y because this is assumed, anything x is assumed to be fixed. Now, if I have that guy now, like I said, if you don't understand, ask question. If you don't understand, ask question. We're doing more of theoretical things today. Okay? If you don't understand, I need you to ask question. Now, if you take a look at what I have right now, so expected value of a B cap equal this. What is the expected value of y? Now, you remember that, recall that if y is xb plus the error, okay, what is the expected value of y? The expected value of y is this. And this is assumed to be 0. Expected value of y is xb. So, because of that, I'm actually going to write xb here to replace the expected value of y. Now, if I write that, this guy and this guy, this is the inverse of that guy. It's going to give us identity B So expected value of that, identity multiplied by that is going to be that. Now, this is how to show that B cap is a random variable. It follows normal distribution with the mean of B. This is how to show that the mean equal to B. That is, the expected value of that equal to that. This is a true parameter, and this is an estimator. Now, I want to derive the variance. Is there any question on this one? Is there any question on how I derive the expected value? Now, I want to derive the variance. Why do we need the mean and the variance? Very crucial in statistical analysis involving linear regression. Okay, now what I want to do now is I want to derive the variance of that. Let me tell you this. You know, when you take a sample, okay, if I ask you to investigate something and you all take a sample, the means you are working on the same area, the mean that you're going to get will be different, because mean is subject to variation. Okay, because mean is a random variable. Anything that's subject to variation is a random variable. Estimator is also a random variable because estimator gives different values. Okay, estimator is a random variable, and anything that's a random variable, we can figure out the mean, we can figure out the variance. Now, I want to figure out the variance of this guy now. Now, the variance of, what is that? X transpose this, S transpose Y. Because B cap, that is what we derive that to be. And I can, because this is a lot, I can say let, because this entity involve a transpose, I can say let M transpose represent this. Let M transpose represent that, then I'm actually going to have the variance of this equal variance of M transpose Y. Who doesn't understand that? What did I use? I used M transpose to represent the whole of this. Why am I using M transpose? Because this has a transpose in it. Now, the variance of this now, if I want to rewrite that, okay, is the same thing as M transpose variance of YM. This entity can be written as that. M transpose variance of YM. Like I said, please pay attention. Some are not paying attention. Please pay attention. I need your eyes on the board. In case you don't understand, ask question. Another exam is knocking at the door. If you don't understand, challenge me. You pay for the service. Now, do you understand up to this junction now? Is there anyone who gets stuck who doesn't understand that? Ask question. Go ahead.
How did you get the other M on the right-hand side?
That's a very good question. How do I get the other M at the right-hand side? M is seen as a constant. Why is it constant? Anything X in a linear regression is assumed to be fixed. It's constant. Okay. Now, you remember in a basic statistics, what is the variance of 3X? Where 3 is a constant, you're going to say, 3 squared variance of S. If I want to write that in a matrix form, I'm going to write 3 transpose variance of S, 3. This is like a way of writing that in a matrix form. Does that make sense now, right? Okay, now, if this is what I have right now, okay, so if this is what I have right now, what is it? This guy is going to say, what is the transpose of my M? This is M transpose is this, right? This is going to say, if I want to get M here, M is transpose of a transpose. Transpose of a transpose with so here, I actually want to find, please pay attention, transpose of all of that. But I want to get M. Okay? Now, transpose is changing position, right? It's going to make this guy to be X, to be this. When you find the transpose of an inverse, it's going to remain inverse. But transpose, this guy, This is going to cancel that transpose. Then they're going to change position. It's going to be just X. Do you see that now? Now, if I now want to, like I said, please focus on the board. Because in midterm 2, it's going to be a combination. There's going to be some theoretical question. Okay? And that's why I want you to focus on the board. Focus on the board. Now, right now, I'm going to write the variance of that equal, okay, now M transpose. The M transpose is this guy. I'm going to write that, okay. I'm going to write that, this, okay. That's our M transpose. What is the variance of Y? Of course, absorption of a module. The variance of Y is sigma squared. You know that, right? Okay. So I'm going to, it's sigma squared identity. Okay, sigma square identity. Then what is M? This guy. Okay, M is that guy. So X, this. Okay, now because this guy, a constant variance, absorption, then this guy is going to move out. Then I'm actually going to have sigma square this. Then I'm going to have this. What do you see? Look at that. Okay? This guy and this guy forming identity. They're going to cancel out. So what do I have? I got sigma square, then this. Therefore, the variance, that is how we arrive at what you see here. Okay? I can write sigma square IN, or I can just simply write sigma squared as that. Okay, so take a look at that. Now, that is how that's how we show that guy. Now, the second one, the Y cap. The second one here. Okay, the Y cap. You know, it said the Y cap followed normal distribution with the mean of this and that. Okay. Now, what is Y cap? Okay. The Y cap, you know, is X B cap. You remember? The Y cap is S B cap. You can remember from the model. Y equal S beta plus the error. The Y cap is this. Then Y cap is X. What is that? S transpose that X transpose Y. Okay. Can somebody remind me for extra credit? What is that? Go ahead. The Hart matrix. Send me a message for extra credit. The Hart matrix. So Y cap is going to be H equal to HY. If Y cap equal to HY, then I can find the expected value. What is the expectation of my predictor? You know what I predict. So it's going to be expectation of HY. Okay? Like I said, the Hart matrix is in terms of X. It's actually fixed, right? Then I'm going to have H, expectation of Y. Okay, so H. So what is expectation of Y is XB. Okay. Now, if you make an attempt, okay, I want to use XB. You know, here I said I'm actually having XB. You're going to see why. Now, if you use the Hart matrix to multiply this guy, how? Okay, you know, I said expected value of this equal, the Hart matrix is H, this. Okay, then this is XB. Right? What happened? They cancel out. What do I have? That is the mean. Which is that mean? That's what we just derived right now. Okay? Now, we want to derive the variance. Okay? Deriving the variance of HY. Okay. The arithmetic is a constant, right? Okay. Based on the question you asked the other time, transpose variance of Y H. Okay? Because the arithmetic depends on X, is fixed. Okay? Now, when you take a look at, and this is a constant variance, this is sigma square H transpose H. Do you know what I want you to do? The transpose of H multiplied by H is actually going to be H. It's idempotent. That's what we call idempotent. So if you want to investigate this guy, you can investigate. Let's investigate. This multiplied by that. What is H? Okay, H is this. Okay. What is H transpose? Okay. What I'm trying to say. Whatever you get there, if you use it to multiply H, you can investigate that. It's going to give you H. That's what we call idempotent. Okay, so here, what I'm trying to say is you're going to have sigma square H, which is this guy here. If you continue to the error, if you do the same for error, okay, if you do the same for error, you actually going to derive that. Now, I want to move. What is the implication of what we're doing? You're going to know. Now, I said something the other time. I said typically. Now, pay attention now. We have two forms of sigma squared. One from the MLE and the other one MSE. The one MSE is the one that you derive using the sum of square error divided by degree of freedom. Now, situation where sigma square is unknown, we use the MSE, the one MSE in practice, where sigma squared is unknown. Okay? Now, and that is why, if you take a look at what I'm displaying right now, this ANOVA table for regression is when we normally use that when we want to test how significant is the overall parameters in my model. I'm going to say that again. If I want to test how significant is the overall parameters in my model, and we normally use ANOVA, we use F-test in regression. Now, let me tell you this. The F-test, you know what F-test is testing? What is testing? Is testing between two models. Please pay attention. F-test tests between two models. In the null hypothesis, is testing that your model fails. It's testing that all the regression parameter is zero. This is why the alternative is saying at least one is not true. Now, in the actual sense, this guy is saying is supporting model without covariate. He's trying to say your response variable does not depend on any explanatory variable. But why alternative is saying at least it depends on one. So this is like comparing intercept model. Intercept model is a model without covariate. You are comparing intercept model with predators. Does that make sense? And that is what the F-test is talking about. Now, you're now going to see something in the F-test. What kind of variance? Which variance are they using? If you take a look at that, they are dividing the sum of square error by n minus p minus 1 to get the MSE. Then it means they are using the other variance, not the one from the MLE. Okay? And at the end of the day, they're going to look at the p-value associated When the p-value is less than 0.05, then we'll reject H0. Rejecting H0 means, the model you are feeding is adequate. The response variable depends on the covariate. That's what it means. Okay, now, that is the ANOVA table that I just talked about. Now, you see what I just said? The H0, the B1 up to that, they are all 0 versus that. That's what you are testing. Okay? Now, like I said, you use this when the variance is unknown. You use the MSC. But what of in a situation where variance is known? Okay? Now, if I now want to conduct statistical inference, please pay attention. Some of you may be wondering, why am I deriving what is the mean of the beta cap? What is the variance of the beta cap? Okay, we need the variance of the beta cap because we cannot conduct statistical inference without knowing the variance of the estimator. I'm going to say that again. If you take a look at this guy, this is an estimator. Okay. Now, if I compute this, maybe I got 0.6. This guy is a point estimate. Okay. When you have a single value of that, it's a point estimate. A point estimate cannot be relied upon. A point estimate could be too high or could be too low. And that is the reason, if we want to make a sense of this, we need to have an interval estimate. But we can never have an interval estimate without also having the variance of B cap. And that was what we derived the other time. So right now, what I'm trying to do is, if I have an intercept, okay, I don't want to have a point estimate of the intercept. I want to have an interval estimate of the intercept. The interval estimate will provide us an opportunity to know how reliable is the estimate. So take a look at this. If you look at the first one, if you focus on only this, that's a point estimate. But if you can say plus or minus, everything here is margin of error. But what is this guy? Sigma B naught. That sigma B naught, okay, sigma B naught is the square root of the variance of B naught. Without the variance of B naught, I may not be able to know the standard deviation of B naught. And sigma Bi, when I say I, could be B1, B2, and so on, also going to be the square root of the variance of Bi. So without the variance of Bi, we may not be able to do this. What we want to do now. And of course, we're going to check from this Z-score. Okay, now that is what I'm trying to say. We derived this guy the other time. Please pay attention. Do you see that? We derived that the other time, right? The variance of B cap. This here has a lot of variances in it. Variance of B naught, variance of B1, because it's a matrix. Does that make sense? Okay. Now, building on that, we can also test hypothesis about a particular, parameter. Okay, we can test an hypothesis of beta j equal to something, or it is not equal to that, and this is going to be there's going to be a z test. Okay, now you can see we've been using z. Can you see z in the confidence interval? Z in the test. We're using that situation where sigma square is known. But when sigma square is unknown, it's going to be a t-test. Okay? Look at that now. What has happened? Sigma square unknown, you can see z has been replaced by t. Has anybody heard about t-test before? Okay, so we use t when the sigma square is unknown. Okay? But the variance of B cap still remain the same. In the testing of hypothesis, it's going to be a t-test instead of a z. Okay? Now, this is a code in R. Like for instance, that is a code in R for if I want to get the estimate of the parameters. Okay, maybe if you take a look at this, what am I doing here? Okay, what am I doing here? I'm running a multiple linear regression. Take a look at that. Okay, one dependent variable. The dependent variable is MPG. I'm looking at the effect of this, and that. There are three predictors. And of course, the result that came out will tell us how significant is the predictor. Okay, you're going to check here the p-value. If I want to know how significant is any of the predictor, I'm going to check that. And if I want to know how significant is the overall model, I'm going to check the p-value here. How significant is overall model? This is for the F-test. Okay, what you see here? If I want to test this, okay, that will be the p-value. The p-value here is telling me I should reject H0, that I need a model with covariance. That's what it's telling me. But the p-value here, they are individual p-value associated with the predictor. Okay, individual p-value associated with the predictor. And on each beta, okay, how do we automatically, this guy here that I said I want to construct a confidence interval the other time, here, this confidence interval, this formula, how do we automatically give me results if you do this? Look at that. It's right, confit MOD. Confit is confidence interval of the regression parameter. Look at that. It's going to give you, this is 95% confidence interval for beta naught, for beta 1, for beta 2, for beta 3, for beta 4. Automatically, Harry is going to generate all of that for you, okay, with a single code, okay? I just wanted to take note of that. Now, we have other inferences that we can conduct, okay? We are at time, if you take a look at this, I'm comparing model without covariance with model with covariance. We also have a way to conduct a test where we want to compare a reduced model with a complicated model. What do I mean by a reduced model? A model, maybe in one, I consider model with 2 predictors. And in another one, I consider model with maybe 4 predictors. And I want to know which one worked better for me. Should I use a model with 2 predictors or should I use a model with 4? Okay, under the null hypothesis, the null HO will support model with 2 predictors, like we support a simpler model, while in the alternative is going to consider a complicated model. Okay, and when you are doing that, and this is an example, full model against a reduced model. I want to know which one is going to work great. With that, I'm going to use a nested F-test. Now, the F-test that I'm going to use is what I'm deriving here. Okay? And at the end of the day, we have a way you can actually do that in R. I can also do a linear combination test. Okay? So all of that, we have that in in R. I don't want to rush you. Like I said, I think I'm going to continue from this page. We're in a week where I want us to slow down a little bit. Slow down. Like I said, there's not going to be new assignment this week. There's not going to be new assignment. I want you to reflect on what you've done. Your assignment for this week is to reflect on what you've done from day 1 up to this moment. This is week 1. This is week 10. You can see time is flying. This is week 10. You are not submitting that. Just review that, okay? And, but I need you to review that is because, you cannot deceive yourself, right? Even you can deceive me, but don't deceive yourself. I need you to review that. If you review from week 1 up to week 10 and you get stuck with a particular week, please reach out to me during my office hour. My office hour is conducted remotely, okay? No assignments in the week. No new assignment. Have a recap on what you've done from day 1. This way I'm going to stop. Show you all stay safe. Have a lovely day. Bye for now, everyone.